Hello and welcome students. I am Sudipta Nath and today we are going to discuss about a new topic on the material science, and the topic is about the lever-arm principles. This is one of the most important topic, as you know, but this is very interesting and not that difficult too. Now, to form a binary isomorphous system from which we are going to deduce the lever-arm principle. So first of all, we have to draw this type of graph. So over here, the left-hand side, it is showing a particular component. Maybe we are considering for component B. I am not giving you any particular name that is for copper or for nickel right now. Later we will discuss about it. And for right-hand side, this vertical line, this is indicating another temperature graph for component A. So obviously you can understand that the concentration of A is 100% over here and minimum, that is 0% over there, as well as for component B it is 100% on this particular line and it is reducing to 0% over here on that particular line. So right now, first of all, we have to construct this diagram in that way. Next, we are going to mark two different temperatures. I have here also not shown the very specific temperature for copper or nickel. Why I am repeatedly telling you for copper and nickel, because the solid solubility for copper and nickel is 100%. That means any proportion of copper can be mixed with any proportion of nickel and vice versa. So what we are going to do, for example, suppose B is having lower melting point over here, which is marked by this blue arrow, and A is having some higher melting point which is marked by this red arrow. So you can see that there is a clear-cut difference between the temperature gradient. Now, this is a solidus line that this is not arbitrarily done by experimental method, by trial and error method. So when we are going to make a solid solution, you know very well that two lines, one is solidus line and the other one is liquidus line. So solidus and liquidus line, they are clearly visible over here. So above this orange line, which is called as the liquidus line, everything is in liquid state, and below this green line, which is solidus line, so below this solidus line everything is in pure solid state. But in between this orange line and green line, it is a metastable phase. So in metastable phase means it is a mixed phase of solid and liquid. So how much solid and how much liquid it is having, that is the main question. So I am arbitrarily taken one particular point in this metastable phase or mixed phase, that is at point P over here. So right now you can see that this is liquidus line, this is solidus line, and I have drawn a horizontal line which is indicating that what is the current temperature of point P. Clear? Maybe we are considering it is at 500 degrees centigrade. Maybe it is at 500 degrees centigrade right now. Now we have to find out what is the relative percentage of component A and component B at point P at that instant. So component B is having 44% and A is having 66% over here. In that way we can find it out. So next, what we are going to do, that we are going to spot point M and point N on this particular diagram. So MP is one region and PN is another region. Important thing to note that MP, which is having one particular part connected to the liquidus line, and NP, which is having another particular part which is connected to the solidus line. Now this solidus line, what is the relative percentage of A and B, that is given, that is 78 and 22, as well as for point M, what is the relative percentage of A and B, that is 38 and 62, that is also given in this particular diagram. It is not arbitrarily done. You have to put it in the graph sheet, and from the graph sheet you have to take the real data. It's not difficult also, it is very easy. So accordingly you can find it out. Now how to find out what is the amount of solid? Okay, so amount of solid we can find out with respect to the liquidous line. That means MP, this portion, this MP divided by the entire length of the line, that is MN, multiplied by 100. So it is lever arm principle or lever rule. Why it is called as lever rule? Because if point P is the pivot point and MP and PN are the two different sides, then if we are going to find out the solid portion, we have to find out the portion which is directly connected to pure liquid, and if we are going to find out the amount of liquid, then we have to consider the portion which is connected to pure solid. That means just the opposite cases. So likewise from here, for example, I am going to find out with respect to A only, what is the relative percentage. So from A only I am going to get the value MP by Mn into 100. So what are the values that you can see? That is MP by plus Pn, because Mn equal to MP plus Pn, that length. Now what is the length of MP? That is nothing but 66 minus 38. So 66 minus 38. 66 is the amount of the component A, and 38 is the relative amount of component A over here at point M. So accordingly we have to find out this value, put this value, multiply by 100 and get the amount of solid is 70%. Similarly, if we are going to find out what is the amount of liquid, then it will be Pn divided by Mn. So Pn means this portion is directly connected to the solidus line or the pure solid portion. So accordingly we can find it out by using this formula that is called as the lever arm principle. So we are going to put this value and get the value as 30%. So together, if we write down these two values, then you can find it out, that amount of solid and amount of liquid. Okay, you can take a snapshot and you can use this formula also. So this is how, using the lever arm principle, if you can draw the solidus line, liquidus line, and at point P, what is the relative percentage of A and B? These are the two components. And what is the correct temperature, and you have to locate M and N properly. So using a normal graph sheet, you can find it out, or you can predict that what could be the amount of solid and amount of liquid in that particular composition of A and B. Okay, so this is how it is done. Simple, isn't it? Thank you very much.